welcome here in Nijmegen at the Cutting Garden. I think it's great to have this event here and the event online. For me, it's the first time that we're ever doing such a hybrid conference type of thing. I find it really funny that at this moment we're also starting up the thing in Lyon. But already, like yesterday evening, I saw in the signal that we're using for chatting that there were also activities people preparing in the US and in Cuba, and there's a lot of different sites in Europe as well. Like Frankfurt was already busy chatting this morning, trying to get the technical stuff organized. So I do hope that all the technical stuff is going to work. I think it's going to become more clear after the break when we're going to merge with the people in Lyon. So that we hope that we're going to end up in the same meeting. Of course, after lunch we're going to merge with the overall program, with all the gardens together, where we have the plenary sessions. So the idea is that we're going to have. So the idea of sitting here is so that we can chat among each other, which of course is obvious now that we have a local presenter. So this is just like a local presentation. But also this afternoon, we should just chat among each other. And of course, if we have questions for the remote presenter, we just pass those messages on. But in the meantime, we could just also chat and gossip about what's going on. We can tell oh, this is really cool, and we wish we had this in Nijmegen, etc. So that's a little bit the idea. It's also planting seeds here for future research ideas, for future collaborations, and be inspired by the things that are happening here, but also the things that are happening elsewhere on the globe, like in Europe, but also elsewhere, so that we can basically get creative research ideas for our future. So our first speaker of today is Arjen Hillebrand. Arjen and I know each other already really, really long, because Arjen.
Say how long?
Yeah, I won't say how long, because Arjen did his master's in physics in Twente when I was a research assistant there. So back then, I helped Arjen with a project on fetal magnetocardiography with a one-channel SQUID system. Arjen moved on with his career and is now working at the VU Medical Center in Amsterdam, where he's the MEG physicist, where he's mainly using MEG to study patient populations. So as such, we don't talk that often, because in Nijmegen we mainly do the cognitive research with the MEG. Arjen has the clinical research with the MEG. But now that we're both starting to develop OPM systems, Arjen's clearly ahead of us there. We've again started discussing, and I'm really curious to see what Arjen presents with experiences with OPMs in Amsterdam.
Okay.
Arjen, the floor is yours.
Yeah, thank you for the introduction and for reminding me how long I've been doing MEG. Thank you to the organizers for inviting me to present our work on OPMs. So today I'll talk a little bit about how we use OPMs in epilepsy, and along the way I'll tell you also about the things we encountered when setting up an OPM system. So first, why epilepsy? Well, for cryogenic traditional SQUID-based MEG, it's the main clinical application. So we see patients, about 100 patients a year with epilepsy. We try to localize the epileptiform abnormalities so that we can tell a surgeon which areas to remove, and hopefully the patient will be seizure-free afterwards. And why do we use cryogenic MEG? Well, it's got a fantastic temporal resolution, got a good spatial resolution with whole head coverage as well. And compared to the EEG, the signals are not disturbed by the skull, so they're not spread out and the amplitude isn't reduced. But there are some disadvantages. But the main problem, I think, is that the SQUIDs are in the viewer, and they are about 2 centimeters away from the sources of interest, which reduces the amplitude of the signals that you are interested in, and also your sensitivity to deep sources. For example, the hippocampus, which is an important area in epilepsy. We often find abnormalities coming from the hippocampus, but they are difficult to see with the traditional system. Also, most SQUID-based systems have an adult-sized helmet, which means that for the small heads of the children, the sensors are even further away from the source of interest. And of course, you're restricted within the helmet. So if there's any movement, you move with respect to the sensors. This causes artifacts, or in case for patients with epilepsy, if they have a seizure with a lot of movement, actually move away completely. Well, they could potentially move outside of the helmet. So you can't, or it's difficult to record seizures with the traditional system. And of course, the MEG system, we've just talked about it as well. It's not cheap to buy and also not cheap to run. So the group in London and Nottingham, they did a simulation study where they simulated what would happen to the signal if you were to remove them outside of the dewar onto the scalp. So you win this, say, 2 centimeters in distance. What would happen to the signal? So here you see the field map produced by a source around the central sulcus. So it's a view from the top of the nose and the ears there. And you can see it's a very sort of spread out pattern that you pick up with the traditional system. And also, if you look at the amplitude, it's about 4.
Can I interrupt very quick? We haven't shared the PowerPoint. Is it okay if I do it quick? So because some people joined, we won't be able to see.
Please have the PowerPoint. Yeah. Share the PowerPoint.
So the amplitude is quite small. So what happens then if you move the same sensors onto the scalp? Well, there's 2 things. The field pattern is much more confined. So your spatial resolution already increases by moving the sensors closer to the brain. And also the amplitude of the signal is increased by a factor of 10. And if you do this for all the sources for different locations on the brain, on average, the increase in signal strength is a factor of 5 on average. The OPMs themselves are a little bit noisier than the SQUID sensors, so the overall the signal-to-noise ratio doesn't increase by a factor of 10 or 5, but still it's an increase with respect to the SQUID system. I mentioned the higher spatial resolution that you can see in the field maps, and of course they're variable, so you can now move your head and the sensors move with you. So you could potentially record seizure activity as well. The technique, the OPMs themselves are, well, affordable. At the moment, it's still quite expensive, but about a third, if you buy a whole head OPM system, will be about a third of the price compared to a SQUID-based system. But I think those prices will come down as more and more centers will start to use OPMs. And I think a big advantage as well is that they are modular. So if one breaks down, take another one from the cupboard and you can continue recording. Whereas if something goes wrong technically with the SQUID system, you have to, well, get an engineer to come over and fix the system if it's a big problem. So there's quite a big maintenance contract on the SQUID-based system. So there's a lot of pros for the OPMs. So how do they work? Well, basically, they're quite small. It's about 1 cubic centimeters. It's the Gen 2 generation of the Q-spin sensors. And this sensor contains a cell with a gas in it. And the properties of the gas change when there's a magnetic field. A laser light shines through the gas. And the amount of laser light that gets through the gas depends on the magnetic field. So that's shown here. The zero magnetic field, all the laser light gets through the gas. If there's an external magnetic field, then the amount of laser light that comes through the gas decreases. So you have a kind of an indirect measure of the strength of the magnetic field. And actually, in the next talk from Lyon by Garrett Barnes, he will tell a little bit more about the details of this curve in about half an hour, I think. Okay, so, well, with all these advantages, we thought, can we get a system going in Amsterdam? You can buy the sensors commercially, but that doesn't mean you have a workable MEG system in a clinical environment. And then once we had it working, we wanted to show that actually the advantages of OPMs compared to the SQUID system for patients with epilepsy. But I'll first talk you through some of the, well, hurdles we encountered when trying to get the system to work. You've probably seen this figure before. So the signals we try to measure are 10 to 100 femtotesla. And then we have all these sort of noise signals coming from the patient or the subject itself. And we have a lot of noise coming from the environment as well. And if you see or look at these noise levels, there's a couple of important sort of cutoff levels. So at 50 nanoteslas, the OPMs can actually work. You can switch them on, and they contain coils that can reduce the field that's the background field or the noise field that's falling on the OPMs. So this is the minimum noise level that you should have to be able to switch them on at all. Then at about 5 nanoteslas, the OPMs get into the dynamic range. So this range, you can actually record some signals. But the background field would still be so large that if you move the OPM through this background field, that causes an artifact and you move outside of the dynamic range. So ideally, you want to have the noise level at 1 nanotesla or lower. So you want to be in the green range, if you like. We started to try to get the system going, and then we had to replace our squid-based system, which has a big advantage that it's got a helium recycler. But this helium recycler gives off a static magnetic field that actually brings your noise level up to about here. So we actually started here in the magnetically shielded room with the helium recycler. We moved way outside of the range where we can actually switch on the OPMs. But luckily, Megan, the manufacturer of our squid system, built us a set of coils around the recycler. When you send the current through these coils, it produces a magnetic field that cancels the field that is produced by this cold head, part of the recycler. So we actually managed to get the noise level back to sort of where we can start doing some other engineering tricks. And for this, I think Niall is also on the schedule later on today. We used Niall's work from Nottingham. They designed a set of coils, again, coils to reduce the noise, where we have 5 panels on each side, and each pair of panels, they sit on about a meter and a half away from the subject. These panels reduce the fields in the different directions and also the gradients in the different directions. And for this, we use 2 reference sensors, flux gates, so they're not as sensitive, but sensitive enough sensors to record this background field. We have this background measurement. We use that to work out how much current should be sent through these coils to reduce, to null the background field. And they've shown that, yeah, with this setup, you can reduce the field by a few orders of magnitude, up to 10 or 15 in general. So with Niall's help, we wanted to build these coils. So we had an external company to route the wire parts for the coils into 2 by 2 meter plastic panels, or 4x panels. And then we had to lay 1.2 kilometers of copper wire to build the coils. So there were a few weeks where actually no one wanted to walk through our corridor, because if they didn't look very busy, then I kindly asked them to put in some copper wire into these panels. So as you can see, there were quite a few people who didn't look very busy. It also helped that there was a bowl of chocolate there, so if they finished a couple of meters, they could have some chocolate. So in about, well, it took about a week and a half, I think, to lay all the copper wire. Then we had our technical department build a frame around those panels. So here you see the panels with the coils inside them on both sides of the subject. And if you then switch on the current through the coils, there's a kind of a virtual box where the magnetic field is really reduced to, well, as close to zero as possible. So that's what we did. What you see on the right here is a recording of 5 minutes, just an empty room noise recording. And as you can see, well, this is the magic 1 nanotesla noise level. When we start recording, we're nicely below this magic limit. But you can also see that after a while, you have these huge artifacts. So this is just fluctuations in the background field in our, well, busy Amsterdam environment. And if you were to record with a subject at this moment in time, they move a little bit, you get artifacts, you get out of the dynamic range, and your recording will be useless. So, well, in a way, it's good news, but we're still not on the green. So we had to do a little bit more. I was a bit disappointed actually, because if you see similar figures from Nottingham, they look much nicer, but they are sort of in a green park on the outskirts of Nottingham. I don't know what it would be here, if your noise levels would be. You're probably similar to Amsterdam, I guess.
I think we're slightly better. Our MEG is at the back of the building on purpose to get it away from the cars. That's a design decision that we made 20 years ago. We have a train that is running about 700 meters away from the London center, but that train is still a diesel train.
Okay.
So what we're afraid of is that at a certain point they're going to switch to an electric train, because then that's going to cause like a very large magnetic artifact as well.
You have to move the energy in this room.
And we might have to move the energy up to this room. Yeah.
Okay. Well, this is what we had to live with. So we had to come up with another solution. So again, this is the situation that we have. We have our panels here, our reference sensors, and the OPMs in this sort of quiet area. But now that we have the OPMs in the dynamic range, we can remove those reference sensors. And then do we have another signal that we could use to drive these coils, these nulling coils? Well, we do, because the OPMs are working now. So we can use the OPMs themselves to pick up the noise fields, and then have the OPMs drive current through these coils. And we can do that continuously. So if the environment changes, if a train passes, then we can just increase the current through these coils and reduce the noise, so that we stay below this magic 1 nanotesla level. How much current should we actually feed through these coils? Well, for this we calibrate the system. So what we do before we start is we send a known current through the coils. We see how the OPMs respond to that. That gives you a calibration matrix. And then when you do the recording, you have a measured field, you apply the calibration matrix, and that tells you exactly how much current should go through the coils. And I can show you how, well, I hope I can show you how it works. It's always a question with movies, but so this is the recording of the background level. So it's about 1 nanotesla roughly. Then we do the calibration. So we pulse the coils. We see how the OPMs respond to that. Gives you a calibration matrix. And then we can start recording. So at the moment, the dynamic nulling is switched off. You can see that the overall noise level is about 4 nanotesla. So it's not good enough yet. But now we switch them on. Feedback kicks in. The scale changes. And now the noise is 100 picotesla, so 1/10 of a nanotesla. So we're very well inside this green noise level. Switch them off. See, it's not good enough. Switch on again, and the noise should reduce again. Feedback loop kicks in, and then the noise level reduces again to about 100 picotesla. How long do we? Yeah. I think we've got plenty of time. I could watch this for the next 15 minutes. I think it's really exciting. But yeah, I've got more things to say. So.
No.
Yeah, I thought it was from your laptop, but it's from the other one. Never mind.
So again, if we do a 5-minute noise recording, you can see we never exceed 200 picopascal. So we can actually, we're at this noise level, so we can actually start our recordings now. And the advantages as well, because the noise level is so low, we can actually record when people move their head as well. So if the patient has a seizure, you should be able to record the seizure activity. Okay, so we have a system, and then we wanted to show the advantage of the OPMs compared to a script-based system. And we didn't make it easy for ourselves. We wanted to show this in the most difficult cases. So we had 3 adults who had temporal lobe epilepsy, so deep in the temporal lobe hippocampus. So these are deep sources that are difficult to pick up. And we have 3 children as well with their small heads. So you should have the advantage of the OPMs there compared to the grid system. We want to show that it would be easier to find the abnormalities because you have a higher signal to noise ratio. So we would expect to see more platform activity and also with a higher signal to noise ratio. And we wanted to show this advantage that you can actually record during movement as well. Well, the methods I've just explained to you already. Unfortunately, we only had 6 OPMs, so it's a very small system. So it's a 2nd generation Q-spin OPM, so they record in 2 different directions. So in total we have 12 channels. We wanted to have the optimal situation for our OPM recordings. So we built bespoke helmets for our patients. So they had an MRI before. We extracted the scalp, we made a model with holders for the OPMs, and then we 3D printed the helmets. And for the data analysis, we applied a spatial filtering approach to clean up the data. We filtered in below 48 Hertz. And we did the recordings twice. So in the morning we did the OPM recording, and in the afternoon we did the script recordings. And we compared the data in terms of the spike yield, so how many spikes we found, and the signal to noise ratio. And as I said, we didn't make life easy for ourselves. These patients had an MEG scan before, so we knew where the signals were coming from. That meant that we also knew where to place the OPMs. With 6 OPMs, we needed to know where to place them. But we made it difficult in terms of the quality of the signal that we expected. And this is an example for one of the adult patients who had bilateral sources of his platform activity. So from deep temporal regions, you can see the spike wave at the top, and also poly spikes. And in color coded here in the brain are regions that show, what's shown is the number of spikes that we found in this patient. So the brighter the color, the more spikes. As you can see, they come from both left and right temporal regions. Then we did the same with our OPM system, and you can see the same spike waves and the poly spikes were recorded. And we also again show that the spikes were coming from the temporal lobes. Of course, the localization results weren't as accurate. With only 6 OPMs, you can't really localize that well, but at least it was pointing in the same direction. So that was good news. And this is an example from one of the children. Again, this was the original MEG scan, so this was the field pattern that we recorded for his spikes before. Spikes were coming from around the central sulcus. So based on this field pattern, we knew where to place the holders for the OPMs. We 3D printed the helmet for this patient. And here you see the results for the cryogenic measurement, showing the field pattern again for one of the spikes. And as you can see, it matched quite nicely with the original MEG recording. And on the right there, you see the pattern for the OPMs, where we projected the data onto the helmet the Swiss system, so they could directly compare the two patterns, and well, hopefully you're convinced we picked up the same signals. So out of those 6 patients, in 4 of them we could actually record a platform activity, and in two of those patients we found more spikes with the OPM system compared to the squid-based system. And for 3 of the patients, the SNR was actually slightly higher for the squid system than for the OPM system, which was not what we had expected. But the effect size was very small, so the difference in SNR was quite small. Still, it was not what we expected, but there's a couple of reasons why this could have happened. I think one reason is that we only had 6 OPMs, so we could have easily missed sort of the hotspot of the maximum signal amplitude. So if the OPMs are slightly placed around these hotspots, you reduce your signal strength already. So that was one reason, and the other one was that one of the patients we actually recorded many with the OPM system, many small spikes that were not visible in the squid system. So if you don't compute the average ratio, it will be very low for the OPMs, but actually the OPMs are doing better because you are able to measure those small spikes. So overall, I'm still quite happy with this result. And also, a final recording was with a patient who was 23 years old, and at the time of the recording, he had 10 seizures a night. So the poor guy had a lot of seizures. That's why we actually chose him, because we wanted to capture a seizure in our recordings. So we sleep deprived him, so he was almost guaranteed to have a seizure during the day. We also had to strap him because he had very kinetic seizures, so a lot of movement during a seizure. So we were afraid that he would actually move so much that he would pull the cables from the OPMs. So the poor guy was sleep deprived, tied up in a chair, and then we recorded. Well, he said we would record until he had a seizure, and well, it took about 2 hours until he had a seizure. So this is in red, you see the onset of the high frequency activity. Then after about 2 seconds, you could clinically observe the seizure as well. He opened his eyes, and then afterwards you could see the movement artifact when he started to sway and rock. But actually, even during that movement period, the signal didn't saturate, so we could still record the signal. At the moment, that part of the signal is still useless because it's full of artifacts, but if you would record that with a whole head system, you can use cleaning techniques to clean up the signal a lot more. So I think that's very promising. And just for comparison, this is at the bottom is a video EEG that was recorded a few years ago, and again you can see the increase in fast activity after which full-blown seizure starts with the movement artifacts. So very similar seizure as we saw earlier. So I'm quite pleased with these results. We've got an OPM system that's working. We can use it in a quite difficult patient population. Children were happy to comply with the recordings. Thinking sort of more long term, it will become a relatively affordable technique. Well, I think it has to be demonstrated, but I think the maintenance cost will be a lot lower. And maybe even in the longer term, it might actually replace EEG, because it's MEG, OPM-based MEG, got increased spatial accuracy compared to the EEG. You don't have this problem with the skull and the volume conduction. We have an increased sensitivity to deeper sources, and it's patient friendly as well. You don't have to glue these electrodes on. You can just put a helmet on and you can start recording. So I think OPMs are really a great opportunity for the future, for not only applications but also for research on healthy patients, on healthy subjects on cognition and in other patient populations as well. Of course, there's still things to improve. We only had 6 OPMs. Again, work from London and other groups have shown that you need about 50 to 100 biaxial OPMs to fully sample all the patterns in the magnetic fields that are coming from the brain. The new version of Q-spin OPMs come with miniaturized electronics, so it really becomes a wearable system. You put all the electronics in a rucksack, and that's your whole system there. I think there's work to be done still on the helmet. We've used these spoke helmets, which is sort of the ideal situation in terms of accuracy. If you're going to run projects with 100 patients or subjects, it will become, I think, impossible to 3D print them. So we need something that's flexible, but yet it should be rigid as well. You don't want these OPMs to wobble on the head. So we need kind of two constraints that are conflicting. You want it flexible, but also rigid. So we have to think of ways of solving that. So this, for example, wouldn't be optimal because a little bit of movement and these OPMs will start to move as well, causing artifacts. For the Q-spin OPMs, the bandwidth is quite limited to about 100, 130 hertz. If you think about epilepsy again, there's a lot of interest in high frequency oscillations, which are a good indicator for the regions that you want to remove. But these oscillations happen at 250 hertz and above, so you can't measure that with the current OPMs. Although helium-based OPMs have a much higher bandwidth. From a sort of working in a hospital, this is still a system that needs, an engineer and a physicist probably to get it going. In a clinical environment, you want a turnkey system where the system just works, the field knowledge just works, all one single piece of software. So I think there's a lot of work to be done there. And of course, you can't use a system like this in a clinical situation if there's no, in Europe, no CE approval for both the hardware and the software. And we're not there yet, so I think that's also something that needs to change. Timing. There's a lot of people who worked on this project. So people from UCL, Nottingham, Megan helped, people from Utrecht, a lot of people from VMC, Q-spin, and we got funding from the Epilepsy Foundation to buy this pilot system to get it going. And I would like to thank you for your attention as well.
Thank you.
I think so far we can keep the questions in the room. So if anyone has questions for now, and there will be a coffee shortly after us.
At the start, you mentioned something about the OPM being more mobile, but now you have this very static box to shield everything. Is it possible to make that also in a mobile way?
Well, good question. Yeah, so these panels, you have to stay sort of within the center of these panels. You have this virtual box of about 40 centimeters cube side length. Mm-hmm. Again, the group in Nottingham are way ahead of us. They have matrix coils, so basically the whole wall contains coils, and you can send currents through different parts of these matrix coils to know basically the whole shielded room. They've demonstrated that they can play ping pong inside the shielded room with no problems. So the current setup is not that flexible, but with changed coils you could widen that area.
Can you also make it? Sorry. Can you also make it smaller? Can you also shield only the head?
I guess you could, but then you have the problem that if you move a little bit, you'll be outside of that volume.
Right.
But I guess if you would keep the patient, the subject steady in one place, then that would be sort of optimal, because then you can probably get a better knowing even in this small volume. So the larger the volume, I guess the less shielding you could achieve. It's a compromise.
Yeah.
Yeah, so at some point you mentioned, so we cannot go to really high frequencies with OPMs, that's a limiting factor. But you mentioned that maybe physicists and engineers can fix that, they can work on that. Is that something possible? Because I thought it was an internal problem that is on the system.
Well, for the rubidium-based OPMs, it's an issue. I think Gareth will talk a little bit more about it later. With the helium-based OPMs, it's not an issue. And also, again, the group in Nottingham, they've shown that you can change the modulation of the OPMs to tune in on different frequency bands. So even with those OPMs, if you do some tricks, you can already become sensitive to the higher frequencies at the cost, I think, of losing the low frequency information. But you can kind of play with you have a limited bandwidth, but you can center it at different frequencies. Not standard, but can be achieved.
Yeah, really interesting. And one more quick question, that's okay?
Go for it.
So you wanted to measure activity from the hippocampus, so it's a bit of a deep area, not so deep. How do you think that the OPMs work really better for deeper sources, or it's not as good as we expected? Because still the signal to noise ratio is quite.
Good question. One of the first slides I showed the simulation results from UCL in Nottingham. If you actually plot the improvement in signal to noise ratio for the whole brain, it's you get the biggest improvements for the cortex, and the improvements goes down the deeper you go.
But there's still an improvement.
But there's still improvement, but I think the main gain is that you can place the OPMs everywhere. So the current systems all have this sort of cutoff right here. If you go further over the temporal lobes, you already win in signal. And if you have willing participants, you could place an OPM at the roof of the mouth to become really sensitive to the hippocampus. That's actually what's done. They've shown that in London as well. But then, not I guess your children will be able to comply with that. So but I think, strategic placements of the OPMs could help you with your signal.
Maybe selfishly asking about the children. So you were saying they were willing to engage in this procedure. So I think there was something like 5 to 6 year olds.
No, actually there were between 10 and 12, if I remember correctly. Yeah.
And so I saw that. So one of the things that I could imagine plays a big role is the comfort of the helmet. Mm-hmm. So I noticed that in the helmet you sort of like have like one line here that separates. So there are like two pieces to it. Is that right?
Yeah. Actually, our first version was a whole helmet, but then we couldn't get it over the head.
Exactly.
It's quite sturdy material. If there's a little bit of a bump somewhere, you just can't put it over there. So what we did is made it in 2 parts. You can put it on and then put it back together again. And that worked, yeah.
Interesting. And does it sort of like hold? Do you need to sort of have a chin strap?
No, there's clips. So there's these clips. They hold it together.
Interesting. So it's just tight enough that you don't need another piece that holds it down.
We did have a chin strap as well, but in fact, I don't think you need it because it was really tight actually.
Okay. Yeah. But so apparently it was not too tight because they tolerated it.
Yeah.
And did you have any I guess when you did you try one on yourself?
Yeah. Well, the first version was we built it for a colleague of mine.
Yeah.
But our head sizes were quite similar, so I've worn it as well.
So does it feel? Do you feel it a lot actually, or does it get warm, or how do you deal with the heat?
Heat is an issue, but with only 6 OPMs, for us it wasn't. I guess if you have it, a whole head system. Well, that's why we have these holes as well for a bit of ventilation. But you would have to, be careful with warming up, I think. with the rubidium-based OPMs, because they get a little bit warm. But if you have enough of them, it gets quite warm.
And would you think that there's a benefit to having the helmet actually being very tight, or is it actually because ultimately you want, I guess, the OPMs, the sensors to be close, but the helmet doesn't necessarily need to be tight, right? Like the plastic part of it, let's say.
You don't want the OPMs to move with respect to your head, so in that sense, well, it needs to be fixated.
Yeah.
But the field line helmet, the pictures that I've seen, is that the helmet is quite big itself. The helmet itself is quite big, but then there are holders that you push through to have the OPM on the scalp. That helps you, I guess, with your ventilation, because you can have a slightly bigger helmet, so there's a little bit air ventilation. But it still would be hold in place because the sensors are sort of keeping the helmet locked in place. Yeah.
I'm just thinking, because you also mentioned this might be maybe in the long run replacing EEG. I was trying to think about similarities, and they have, for example, if you have these like nets, they essentially have the pressure to put the electrodes down with the sort of like net pressure of the elastofix or whatever they're called. So I was just wondering if there's, and that went a little bit in the direction of what you were showing in this like one example.
Yeah.
But I guess then that doesn't stay in place.
Or it will stay in place, but I think the problem is that the OPMs will wobble a little bit.
Okay.
The wire, you have to the wires to the OPMs are quite heavy, relatively heavy.
Yeah.
So a little bit of movement will actually cause the OPMs to wobble a little bit. And then if you have only a wobble of a few degrees, you already get quite a big artifact. Yeah.
Sorry, after another question. I should give other people
the get a really quick break.
Okay.
We have 5 minutes till the next one from Lyon.
Okay, let's start this hybrid symposium. So between Lyon and Nijmegen. Is it working, the microphone? Yeah, okay. So first of all, I want to thank you, the organizer of this event, especially Alexandra and Françoise, who are the origin of this OPM symposium. So you all know that we are in a technological revolution in energy with this new sensors, the optically pumped magnetometers working at almost room temperature. So in fact, with respect to the last talk, we are really going in the right direction, getting rid of cryogenics and all the constraints linked to the old energy technology. So this morning we are very lucky to have 5 experts in this domain. And we will start with the first talk with Gareth Barnes from University College in London. You are professor, head of the energy, and you contributed to a lot of different fields in the energy, and you especially OPMs.
Thank you very much, Denny. Thank you very much to the organisers. It's a fantastic event. It's a real pleasure to be here. Hello, Nijmegen. Can you hear me? So I'm going to talk about OPMs. And I'm going to start with my last slide and tell you what I think is exciting about them. I've got one here in my hand. You can put them directly on your head, okay, so you can get the maximal signal from the brain for any head size. That makes them really exciting study human development. Because you can put them on your head, you can move about with them. And that means we can start to study people as they interact with one another naturally, nodding their head when they agree with something, for example. Social interaction. And importantly, we can start to scan people for a long time. You don't have to ask people to lie still for 10 minutes, don't move. You can actually, they can wear these helmets or these OPMs for a long period of time. So suddenly you can start to think about different time scales for experiments. Both of these things fit really nicely into I think what the main and exciting clinical application of OPMs is, and that's application in epilepsy. I'm not going to talk about that today. So I'm really excited to hear what the other speakers have got. And of course, because they're small, you can put them anywhere. Okay? So there's loads of new things from the brain and the body that we can make. Really, it's just Lego for biomagnetism. Okay? You can build your own MEG scanner, these little building blocks. Okay, I'll start off with just to give you an overview of how I see OPMs working. That's from somebody who's not built an OPM himself. I'm a user. Then I'll talk about what stuff we've done in London, how we started moving around with OPMs on. And then the last bit of my talk is telling you about how we can put the sensors just about anywhere. So all this comes from, we started off doing MEG, magnetoencephalography. We're measuring tiny fields, about 100 million times smaller than the field we're all in now. And we're using these amazing sensors called SQUIDs, or superconducting quantum interference devices, to measure these tiny fields from the brain. These are great sensors, but you have to keep them super cold, so you have to make them in the bath of liquid helium, and that means MEG systems are essentially big thermos flasks. And you have to make the thermos flask a little bit too big for everybody so you can fit lots of heads in it. And that's the main disadvantage of this, although SQUIDs have done tremendously well, is that you really want the sensors to be as close to the brain as possible. If you get them twice as close to the brain, you'd have 4 times the signal. So the first time I heard about wearable OPMs, or OPMs in general, was from a talk from Svenja Knapp, talking about work she'd done with Tilman Sonder in Berlin. And Svenja and her colleagues at NIST in Colorado, what they'd done is they developed atomic clocks, miniaturized atomic clocks. Then what Svenja realized was these atomic clocks have got all the same ingredients you need for a very sensitive magnetic field detector. She was able to put together these tiny sensors which you could put really close to the brain. And you can see the comparison they did between SQUIDs and OPM sensors. Notice this is now a somatosensory evoked field, and the top is the SQUID and the lower panel is the OPM. What you notice, the OPM is a bit noisier, but you also should notice that the signal from the OPM is a lot bigger, about 20 times bigger than the signal that is measured with the SQUID system. And that's simply because Svenja and Tilman were able to get the sensor a lot closer to the scalp than would normally be possible with cryogenic systems. So this is really exciting, and this is already over 10 years ago. It amazes me how quickly the technology has come on since. Just to give you an overview of how OPMs work, how I see OPMs working. There's 3 essential ingredients. You need a laser, a gas, and a photodiode. You shine the laser through the gas, and at 0 field, the laser goes straight through the gas and hits the photodiode. There's no loss of laser light. Okay? The idea is the lasers put all the electrons into an excited spin state in the gas, and at 0 field, they'll stay there. If you perturb the field across the gas, then you get less laser light photodiodes. You get less output. So you're working either side of this peak of this curve. Important things about this curve is that 0 really is 0. That's 0 magnetic field. Okay. And the other thing about the curve is that the tightness of the curve essentially tells you how sensitive, how much output you get per change in field. Typically, we have to demodulate the peak, so you know what's positive and what's negative. So you're essentially left with a gradient, that pink line there. So the steeper that gradient, the more output you get per change of field. And you can see then, so the tighter the curve, the more sensitive the device. Okay? But that gradient is directly governed by the time constant of the gas. Okay? So if the electron spins in the gas change relatively slowly, you get this integrative effect. So long time constants give you high sensitivity. Okay? But if the gas changes relatively slowly to magnetic field, then you get lower bandwidth, useful bandwidth from the sensor. So you're trading sensitivity against bandwidth. The other thing, of course, is that you need to be able to use this sensor. And so there's a useful dynamic range, because if you look here, when you get to plus or minus 100 nanotesla, you're getting nothing out of this sensor. There's a useful dynamic range of the sensor. And you'll notice here that that's also related to the tightness of the curve. So the tighter the curve, the lower the bandwidth, because of the higher sensitivity, but also the lower the dynamic range. So the more fiddly you have to be with the environment in order to get the sensor to work. You contrast that with maybe another kind of OPM, where you have maybe less sensitivity, but you trade that for much higher bandwidth because the time constant of the gas is smaller, or the gas changes more quickly, and you have much higher dynamic range. So you can use this sensor in many more different environments. That's essentially the OPM trade-off. You're trading high sensitivity against dynamic range and bandwidth. Of course, what we'd really like is a sensor that gives us all of this: sensitivity, dynamic range, and bandwidth. But then we're back with the squids again. Okay, and squids are really brilliant sensors because if you can lift them up, you can put them on a plane and fly them anywhere in the Earth's field, and they're super sensitive because their response is periodic in applied flux. Now, what I guess I first came to realize how brilliant squids were when we first started using OPMs, and we first started using them in a traditional MEG shielded room. And what I was really surprised about was that the OPM, we had real trouble operating the OPMs in this room because I thought a shielded room would shield the magnetic field, external magnetic field. But of course, these rooms weren't designed to shield static magnetic fields because the squids don't care about the static magnetic field. They only care about a fixed operating point. And so what Arjen Hillebrand has just talked about, hello Arjen, in Nijmegen, is how to refit, how to refurb or retrofit one of the classic MEG shielded rooms with these cores designed by Niall, also in Nijmegen, and his colleagues, in order to operate these OPMs in a classic MEG shielded room. And the idea of these cores is they null the background field and gradients. You can start to operate these OPMs within a traditional shielded room. At UCL, we've kind of spent the money and we've got now a bigger room. It's surprisingly spacious for central London. It's 3 by 4 meters. There's nothing in it, just a subject and some OPMs. So it's very attractive from that point of view. You're not encumbered by any bulky neuroimaging equipment, just the furniture you want to put in there, non-magnetic. Okay. And the nice thing about the room is that within the center of the room, because it's been designed specifically for OPMs, we're less than 2 nanoteslas of static field. And that means we can move these OPMs around the central meter of the room and still keep them operating within their operating. That said, we are in central London, and no amount of money can protect you from the environmental noise in London. So we have the tube going directly underneath our building. This is the tube going past. Similar changes in field when cars go past outside the building. If you move the sensor within the room, this is moving it by about 0.5 meter. You can see the changes in field you see. And if you move it much outside the central cubic meter of the room, you start to see the sensor saturate because of the analog to digital converters we use to get into the computer. You can look at the magnitude of the signals of the noise we're dealing with, even in this well-shielded environment. We're talking of field changes of a nanotesla here due to noise, but we're trying to measure a neuronal signal of 100 femtoteslas or so, which is about 10,000 times smaller than these environmental changes. I'm not going to talk about how these changes have been mitigated, but basically Tim Tierney and Steph Meller have mitigated all of these issues to the degree that we don't have to, well, at least I don't have to worry about them anymore. So it's amazing physics has gone on here to get these sensors working while people are moving within the room. Just to give you an example of this, this is work done by Rob Seamer and Nick Alexander. And what they were doing, they were just giving a standard auditory evoked tone to people while they wore these helmets in the middle of the shielded room. The people were either sitting, standing, or they're standing and moving around with a helmet on their head. They're moving by around 1 meter. That's 100 times more than you'd move in a conventional MEG or fMRI experiment. But you can see that the estimates of electrical activity in the brain are qualitatively very similar no matter what the subject was doing. So it's a really nice confidence builder that actually we can use OPMs even when the subject's not very compliant at all. We can still get our traditional signals for people who inclined to move around quite a lot. Changing things around a bit, rather than treat movement as a confound, what George has looked at is seeing if we can just observe people and see if we can map what's happening in their brain based on simply observing the limbs moving. And this is the person doing the hokey cokey. I believe European translation would be hokey pokey. Yeah. And what the person is doing is they're doing a dance in the shielded room. And if you know the hokey cokey, it involves putting your right arm in, right arm out, in, out, shake it all about. And you can see the decoding on the left is done by a hidden Markov model, which is just decoding this multivariate data from the subject's posture and working out which particular dance move is going on. As you see, the subjects, there's lots of wires here, so we can't do the turn around, but for the hokey, when you do the subject's waving both arms at the end. But you can see here what we get from this is a design matrix that gives us some way to probe into what's happening, to probe the subject's brain in order to decide which bits of the brain are moving, which bits of the body. Now, you just think about this for a moment in the context of normal neuroimaging. How would you do this normally? How would you do a somatosensory map normally in your imaging? You would ask people to lay still, don't move your head, and minimal movement, okay? But what George is saying to people is, get up and dance, please. Okay, so it's very, very different kind of paradigm here. What we find from this is that we can see, as you might expect, you can see very clearly the arm movements, but the legs don't really work out as well as you'd like. And if you try to do the hokey cokey, and when you do have to wave your right leg or your left leg, you do find there's a lot of other things involved. Okay, and I speculate that might be one of the reasons. But it's interesting and exciting that now we're looking at real whole body movement. You get the subject to sit on a chair when they can move their arms and legs while still sitting, then it's all fine. You get the legs more medial, the arms more lateral, and all the lateralization works out. So that looks like what we'd expect from a conventional neuroimaging experiment. But maybe the plots on the left kind of more exciting and lead more towards natural movement. Final thing about OPMs, of course, as last part of the talk, is we can put them anywhere. Really exciting work from Arizona, where people are measuring action potentials from peripheral nerves. From Denmark, where people have built an OPM array to look at retinal electrophysiology non-invasively. And in London, where we've tried sticking the sensor in my mouth in order to look at the hippocampus and look at deep brain structures. Now, related to the hokey cokey, of course, as I was saying, when you're doing this, there's a lot of things going on to keep me from falling over. And a lot of that processing is done by the spinal cord, for which it's very difficult to get the electrophysiology, at least non-invasively. So that was our next target. We're inspired by groups in Japan who've built a cryogenic MEG system, cryogenic MSG, magnetospinography system, look directly at the spinal cord. And what they're able to do, they're able to map action potentials traveling up the cord with amazing resolution in time and space. We're not there yet with OPMs, but we have got a 3D printer. And so we can now start to say, well, what would happen if we measured from the cord and the brain at the same time? This is how we started off, brain and cord measurements, but then began to realize it's a much more tricky problem than I'd originally thought it was. The cord, it turns out, even though if you feel the bony bit, I think that's where your spinal cord is, actually 4 to 6 centimeters deep within your body, and it's also wrapped in muscle. So it's a very challenging structure to image with anything, especially MEG, especially biomagnetism. But Megan and Sven, who's the one on the bench here, anonymous, have really persevered with this. And what you can see is now we've got a system where the subject is lying down, and that's to minimize back muscle movement. We've got OPMs around the sensory cortex and around the cervical region, around the neck region. And what the subject is doing here, they're following a force trace on the ceiling with their thumb muscle. And if you look at what's happening here, these are initial results, but what looks quite exciting is if we look at where the power is concentrated from this thumb muscle contraction, it seems to be in the right region. It should be roughly where the neck touches the shoulders. And you can see we're getting there, we're getting towards that in these subjects. If you take that region of peak power, then you have an estimate of electrical activity over time, and you can see how that compares with electrical activity that you're measuring from the brain. And you can see now we've got linear phase, we can see phase relationships between the brain and the cord in these 10 to 20 hertz bands. And we also see these envelope-to-envelope relationships in similar bands across subjects. So it's just really starting to open up what's possible with OPMs. We've not only got a window onto the spinal cord function, how it interacts with the brain, but also, of course, we've got a window on the spinal cord and how it interacts with the muscle, and we know already about the muscle and the brain. So we don't know quite how we're going to analyze these data yet, but we do think it's very, very exciting that we've got this window, and there's lots of potential there to further explore the whole neuroaxis now with OPMs. Just to show you where we're going, the thing that doesn't appear on ground applications or simulation diagrams is all the wires. That's been the biggest problem for us. And in UCL, this is what the system is at the moment. You can see all the wires leaving the subject, relatively heavy. They go out of the room, and then this huge rack that's about the size of Steph who's standing there. What we're trying out at the moment, though, is a new system design, in which all of the rack, that's the same Steph in both pictures, but the whole rack is now replaced with a small backpack, and there are just 2 wires leaving it. And so it's very exciting for the future that I think a lot of the wear and tear and the general reliability issues with the sensor, I think, will go away, because a lot of our problems have been with the wires and not so much with the sensor. Very exciting. I think there's at least, within 10 years now, there's at least 30 OPM neuroscience groups worldwide, and at least 4 commercial OPM manufacturers. There's loads of, the field is moving very, very quickly. So this is how we started. What's exciting about the OPMs? Maximal signal for any head size. Okay, you can move about with them, and you can put them anywhere. And it's Lego, it's all of your favorite things, Lego and biomagnetism all combined. Okay, I'd just like to thank all of my funders and co-workers and the team, and thank you for your attention.
Thank you very much for this very exciting talk. Some question, Gareth?
Thanks, Garrett, for a great talk as always. Can you comment on of having personalized casts for people, and how you achieve that, and how much it counts?
Yeah, well, so I mentioned the wires, and I think that's the main reason we've got these. As Christian says, we build personalized head casts for each participant, and one of the main reasons for that is the wires that when they move across one another, they tend to interact electromagnetically. We have to keep them all tidy. And in young epilepsy, I showed a picture earlier, they've gone down a slightly different route. They use a solid helmet that's generic, lots of people. That's also really good, but then you get this, similar issues you have with traditional MEG, where your helmet wobbles on the subject, and you lose sensitivity on a lot of people. So I don't know what the ideal solution is at the moment, but I do think that this interaction between the wires, if that were to go away, and I think it's getting minimized now, then you could move towards more flexible arrays, much like an EEG cap. But at the moment, it's true, it's very expensive. I mean, we've spent so much money on it now that we've got a library of these casts, and so what we tend to do now is find your head double, find somebody who's got the same head size as you, and make them wear that helmet. But it's been a huge expense, and I hope it's been worth it. But we'll see.
We have a question. It's maybe a little bit related. When do you think we will be able to buy a complete MEG system commercially?
Well,
Sorry.
I think people are selling them already. I mean, Circa sell them, and Fieldline sell them, and Etienne, you selling complete systems? Yeah.
Yes.
So
The main point, in fact, that for us, the systems are not yet completely certified from. So it's true that we may have difficulty to obtain ethical approval or some.
I think that's
some
right.
detail.
I mean, I don't know. I mean, thankfully I've managed to stay out of the company, the commercial part of this, but it has made me appreciate the classic MEG system that is all certified and it just works, and you just appreciate now how much work has gone in, 30 years of work gone into the system, the classic grid systems that work all the time, very robust. So I don't know. I really don't know how long. I used to say 5 years, but that was 5 years ago.
Thanks.
And now it's time to have Tjerk Gutteling. So Tjerk did his postdoc with Ole Jensen, working on attention and oscillation in the Donders Institute first, and then in Birmingham. And for almost 2 years now, he's with us in Lyon, and he's our expert in analyzing OPM data. So let's welcome Tjerk.
Thank you. Welcome. Thanks for being here. Also, very nice of the people in Nijmegen to join. Leuk dat jullie er zijn. So it's my pleasure to talk about what we've been doing here in Lyon with the OPM sensors that we have here, and just basically share some results with you that we've obtained in the last time. Mostly on healthy volunteers. So, as Gareth has explained, the majority of the OPMs, they all use a certain type of gas. Most of them use an alkali gas to operate. And while this works very well, they're very sensitive sensors. They have a few drawbacks, such as they need to be significantly heated to a degree to reach their optimal state. And usually they're on the side of this trade-off that also Gareth has talked about, where you choose a sensitivity over, for instance, dynamic range. And for that, you end up with a sensor that indeed has sort of a very limited range. And this can, of course, be amended by using either the fixation of the subject or a strong or more advanced shielding. The helium OPMs that we've been using, not surprisingly filled with helium, are sort of on the other end of the spectrum. They're developed by a company we've been working with called Mag4Health. And one of the nice things about these is they operate at room temperature, so they don't require any heating, they don't dissipate any heat. And this is also especially nice when you're using a large amounts of sensors, but also has the added benefit that you do not need any additional insulation between the sensitive element of the OPM and the scalp. So you can basically push them right up to the scalp, and it just gives you just a little bit extra closeness to the scalp. As you can see here also in the picture, the glass cell element that you see there can actually just move right up to the scalp. We work in closed loop mode on 3 axes. This is a benefit, for instance, for the reduction of one of the common errors or sources of noise that you have with OPMs, which is that other axes can bleed into sort of your sensitive axis called the cross-action prediction errors. And one of the key benefits is that they have this huge dynamic range. So that enables you to basically have movement, more movement, tolerance for movement, or magnetic shield fluctuations without them saturating. And they are natively triaxial. We have 3 axes of measurement. However, there's never a free lunch, as Gareth also alluded. It's always a trade-off in this case. And in this case, you do have a lower sensitivity with these sensors, especially compared, of course, to the squids, but also the alkali OPMs. And furthermore, this sensitivity on 2 of the 3 axes is very decent. And the third has a lower sensitivity. So the closed loop operation reduces a lot of noise, but also can actually introduce a little bit of crosstalk between sensors. However, this does not necessarily have to be a problem because it can be characterized and removed. And of course, if you have this huge range of operation of magnetic field, you also will actually record a lot of movement artifacts. And as you can see in the scale here, this is what a sort of typical raw data sample looks like. On 3 axes, you see that somewhere in here is a tiny bit of brain signal buried that you have to get out. So we will need quite some advanced post-processing to get decent results out of this. This is one of the challenges. So we subjected these OPMs to a number of paradigms that we use, also the medium nerve stimulation, which is also a classic in OPM research, a visual task, a mismatch negativity task, and motor task, which of course is also quite important for OPM research for the reasons stated before. So this was our setup. Not quite as advanced yet as Gareth has shown us with a full head, but that will come later. We had 4 sensors for all these experiments that I was talking about. We had 4 sensors on the head, and one was mounted as a reference sensor on above the head. And these were mounted in a semi-rigid helmet that basically should fit all and can actually expand and shrink a little bit per subject. And this was the, well, basically our cable problems. I think everybody has cable problems. This was at least our primary solution for the cable problems, but also, again, this is the first iteration, which is clearly not quite optimal yet. You can see that all these things start out in a sort of duct tape stage that eventually you grow out of and will get better. But this is usually where you begin. So I'll talk about the first results. We did all the sessions both in SQUID, the classic MEG, and in our helium OPMs. And for the sensor stimulation paradigm, we've chosen left central positions for the sensors. So we did median nerve stimulation on the hand, right hand above motor threshold, about 800 stimulations for a group of 17 participants, and we had these 2 sessions to compare. As for processing, we actually did not do any very advanced processing of the signals. So basically just was a bandpass filter with some line noise removal, very conservative ICA because we only had 5 sensors. And most importantly, we regressed out the signals from the reference sensor, and that actually cleaned up quite a bit of noise. So as we first look at the classic SQUID-MEG results, you see sort of a normal evoked field. We put the results of the OPM underneath it, and you can see that there's actually a high correspondence over time between these two modalities. And we've color-coded the traces to the locations and corresponding channels. And as you can see, the middle channel is the radial axis of the OPM. That's the axis sort of going straight into the head. And at the bottom, you see a tangential axis, which is tangential to the head. And as you can see, the amplitude of that axis is a little bit reduced, but actually the signal-to-noise ratio is not quite as bad at all. And of course, the first thing you see is that we have quite a bit of amplitude increase for the OPMs, about a 4 to 5-fold increase, and very high correspondence in time course. You can see that also if you lift out one not particularly representative, but slightly cherry-picked subject, and you overlay the sensors and you scale them to the same size, you see that the correspondence in the time course can be really, really high under sort of optimal circumstances. This gives us at least a good amount of hope that, you know, under the right circumstances, these things can be about equal in signal. When you look at the overall group SNR, so the signal-to-noise ratio, you see that the overall it is a bit lower than what we find in the classic SquidMAC system. However, it's not quite an order of magnitude difference. So we also did a visual task, looked of course at the occipital sensors. This was a very simple task where you were presented a Gabor grading, had to do an orientation discrimination. So we just looked at just the visual onset of the Gabor stimulus. And what you see with the SquidMAC is sort of a classic deflection at 100 milliseconds, as you would expect. And the same thing for the OPMs. However, you can also see this is quite a bit noisier, and this is probably due to the placement and probably the cables. As you can also see this reflected in the SNR, which is quite a bit lower in this case, unfortunately. But however, what we're actually really interested in how this would translate at the time frequency spectrum, this task, as a, you know, just a grading usually evokes some gamma activity with a reduction of alpha beta. So you see this, of course, very nicely in the SQUID results. For the OPM results, this was quite a bit reduced. However, as you can see, traced in black, we still found significant the sort of increase in the gamma range and a decrease lower frequencies, which is hopeful that would at least also be able to look at oscillations in the future. However, we think with optimization of the placement, for instance, it would be a lot better. However, this is already nice. These results were all published before, so you can look them up in the paper. This is so far unpublished. So we did an auditory mismatch task, which is also very simple. You just have a sequence of tones with sort of an irregular presentation of a slightly different tone. And you compare the sort of the evoked field of these two to get a sort of deflection that represents this mismatch you expect. The nice thing about this study is that the SquidMAC was recorded with EEG simultaneously, and there was a separate OPM session. So for this, we had a slightly different montage, also including a frontal sensor with mostly left, central, lateral sensors. So for the EEG results, you see quite clearly between 100 and 200 milliseconds the auditory mismatch. I have to say this is already a subtraction of the activity evoked by the standard and the sort of the oddball irregular tone. So this is subtraction. We then look at the other modalities. You can see that again we have very high similarity Of course, the polarity of EEG and MEG can be quite different. You can see that especially in the radial direction, we have very, very high correspondence of signal. And in the tangential direction, there seem to be actually picking up maybe some slightly different components that also occur in the EEG that we actually don't see in the SQUID and the OPM. Furthermore, for this, we're actually pleasantly surprised to see that the signal-to-noise ratio was almost comparable to the SQUID, except for one subject with apparently responds quite well to the in the SQUID, at least a bit of an outlier. But we're quite happy to see that for this task the SNR is quite the same. So finally, and this is of course always the biggest challenge, especially as I said before, we don't have a shielded room with active shielding, and so any movement that is being generated will actually show up in the data and will create large artifacts. So I had a task where I have a reaching task with a joystick, and we mostly looked at the beta band activity either locked to a visual cue, which instructed to move, or the offset of a reach. And usually when you get a visual cue, you have to perform an action, see a decrease in beta band activity, and when the action is over, you see sort of an increase back again to sort of baseline levels. And of course, we'll show some nice motor artifacts. So the SQUID-MAC system shows sort of the classic reduction in beta band activity, as you would expect. We see the same thing in the OPMs, but again, it's somewhat reduced, unfortunately. But it is still quite robust. Now, looking at the part of with the most movement, you see that this is actually not quite an issue in the SQUID, but in the OPMs, we see that we have large artifacts in the lower frequencies that show up even if we regress out this reference sensor. And thus we cannot completely eliminate, at least at this point, the movement artifacts that are being generated. However, we do see an increase in beta band activity over time. However, we're also not just interested at looking at the power of beta over time, because as you know, beta band activity has been known to occur in bursts. And this, you cannot just look at the sort of mean power of beta, but also at the rate of bursts that occur during this task. So we also calculated this. So we see that here from the top for the SQUID system and on the bottom for the OPMs. As you notice that actually this was we didn't really even find that much going on in the SQUID system. Looking at the overall burst rate, we do see some in for the OPMs, at least for the good axis. But we performed another trick, and if you're interested in that trick, please attend the session on Friday, and there's also some posters that go into this in detail. It's a very interesting analysis. You extract all the bursts that occur during the task and use PCA to look at the different shapes of these bursts that occur in the task. And by selectively picking out a certain shape of the waveform and looking at the burst rate for this waveform, you actually get slightly different results. So what you see here is the mean burst waveform for the OPM data for the lock to the visual cue and the motor, so the reach offset. And you see there's not a lot of task modulation. When you look at a specific waveform, such as this one, you see that this one is actually quite reduced after the visual cue, as you would expect from beta, and you see a quite large increase again after the movement onset, even though you can see there's still quite a bit of the movement artifact still occluding around the motor offset. And these waveforms can be differentially modulated by tasks, such as this one, which is not quite modulated by the visual cue, but more by the motor part of the task. So this, for us, is very nice that we can see that with the OPMs, we have enough accuracy to typify beta burst waveforms as modulated. So despite actually still having sort of pretty poor noise reduction techniques. So to wrap up, in general, overall the task, we see that the SQUID and the OPMs show quite high similarity. The RFs are reliable and similar. The oscillator activity is reduced, but it is robust. We can find good activity and so even waveform shapes. In general, the amplitude is a lot higher, but as of now, the SNR signal-to-noise ratio is a bit lower. This is mostly due to sort of the first iteration of the setup, and of course, cables. And the helmet, the support. I think that's what most people are struggling with to get this optimal, because having OPMs move relative to the head is quite detrimental to the system. Of course, we only recorded this with 4 sensors, and that actually precludes you from using any very advanced noise reduction techniques. So this was basically a bit of regression and filtering. So in that regard, we're very happy to be working with a whole head system now on. Actually, this arrived just last week. This whole head system has 48 sensors that can be placed, and as you see, cable management. Very thin cables. I guess OPM people get very excited about cables. And also these are able to auto-localize, meaning we can get an automatic readout of the sensor positions, which is also a key benefit in reducing the noise. Because with this amount of sensors and having a good characterization of the positions, you can get a better estimation of the noise subspace, and you can subsequently subtract that. And then we can use one of the advanced correction techniques that are being worked on. And of course, we can estimate sources. And who knows, you might be able to dance the hokey cokey. This is just a sneak preview of what we did last week for just a single subject with this system. We recorded again the somatosensory evoke potential or field. And as you can see here, we're now actually able to source localize it and plot at least a topo map. And this actually looks quite well for a single subject. And actually have been able to source localize this to, say, a rather plausible position on the head. So we're quite happy with that. Not quite hokey cokey happy, but quite happy. So this was very much a group effort. So I'd like to thank all these people, my colleagues, and the people from Mac for Health for enabling all this. And thank you for listening to me.
So now it's time for a few questions. Actually, I have one for you and for all the, Gareth, where are you? Yeah, you are here. I was about the spatial resolution of these sensors. How many sensors should we consider? And I have this question in relation to the talk by Maximilian, because one of the disadvantages of MEG data is the huge volume of data we produce when we analyze them. So could we consider having reduced volumes if we need less OPM sensors? I don't know.
Actually, something we should still find out. We can, of course, that's a nice thing. We can move them around. And for instance, what you just saw, we had them spaced out as much as possible. We can also create a very dense array sampling just a little part and see if that actually improves spatial resolution. Of course, it depends on the field of view of the sensor. And of course, the closer you get it, the smaller this field of view may be. But overall, this is something to figure out, or even reconstruct.
Anything you would like to add?
Yeah.
Thank you for bringing the microphone all the way over here. I don't have anything very insightful to say. So it clearly is that the more OPM sensors you have on the head, the better. But as we've seen, the wiring, and it's a big issue. But then again, a big ecological cost is the amount of time people spend analyzing the data, and how many times you're going to do the same experiment again. So I mean, that's one advantage of having a lot of sensors. And also in terms of the noise reduction, as you just talked about, when you've got more sensors, you can make better use of that data because you have a better idea of what the noise in the signal subspace is. So having more sensors may save time and energy in the long run. And of course, there's no helium involved. Well, sorry, there's only a little bit of helium involved now. So I think ecologically, it's already going the right direction.
There are other questions from Lyon.
Maybe I have a comment on that. Is because you are closer to the brain, probably you have a higher spatial frequencies, and it's really a matter of sampling and Nyquist frequency in the spatial terms. So I'm afraid, I don't know, that's a question to everybody. You need a lot of sensors, at least in the region of interest.
Are there questions from Lyon again? Okay, so let's
maybe. Can you hear me?
Yes.
Can I do a quick question, maybe?
Yeah, sure.
Okay, so I wanted to ask if there is any study comparing helium-based with rubidium-based OPMs. And for example, the studies that were presented now, they were mostly focusing on low frequency bandwidths, I think, like beta burst. So I guess this could be better identified with rubidium, maybe, OPMs.
I think actually helium OPMs have a very large bandwidth, actually go up quite high. Is it on? Yeah, sorry. So actually, I think this is not something that is a downside of the helium OPMs. How well the alkali OPMs perform in this, we would have to directly compare, as I don't actually know. It is something that we would very much like to do, to use exactly the same paradigm or subjects even to compare these different systems and see how they perform. But certainly we'll also look with this whole head system at more high frequency oscillations as well, not just gamma, but also say visual frequency tagging, where we can probe the frequency response over a wide range, for instance.
And another quick question. So during the comparison, you chose 4 sensors from the squids and 4 sensors from the OPMs. Since the squids are more densely, the sensors are closer, and they are more than the OPMs usually, because OPMs limit around 100, while the squids could be until 275, 306 or more. Would it be a better comparison to use maybe more squid sensors to have a more direct comparison? And why did you choose the same 4 and 4 sensor?
Well, I mean, obviously the squid system has a large number of sensors. If we were to pick the best sensors out of those, you would automatically already have an advantage for the squid system. On top of that, of course, the CTF system that we used for this is already a fully developed system with noise correction and gradiometers. So the results coming from the SQUID system are, even if you pick out a single sensor, probably, already at quite an advantage in terms of noise correction and relative to the OPMs. So I don't think it's an unfair comparison picking 4 SQUID sensors that are at the same position as the OPM sensors that we use. It's probably more the other way around, that the OPMs are quite at a bit of a disadvantage relative to the SQUID system.
Okay, thanks so much.
Okay, so let's move to the next talk. Thank you, Chair.
The next speaker is Christian Bénard from INS in Marseille. So you are head of the Dynamap group and specialist of simultaneous depth recording and MG recording on other recordings. Thank you very much.
Thank you, Denis. Thanks, everybody. So good for not presenting me as a specialist of OPM, which I am not. So I am kind of the non-specialist in this session. And I'm presenting on behalf of Jean-Michel Badier, who actually did the work I'm going to present in collaboration with the people in the room. So I'm gonna talk about interictal spikes in epileptic activity measured on helium OPM together with intracerebral EEG. So I come from the Marseille MEG platform. We are located within the hospital, the Timon Hospital, which is a very nice location to be not only to interact with the neurologist, but also to perform the simultaneous recordings I'm going to talk about. So we have, as we are a big epilepsy center, we have access to intracerebral EEG, which is obviously performed only for diagnostic purposes on purely medical ground, but that gives us access to recordings within the brain. And this is SEEG technique. That means the electrodes are implanted targeting deep structure of the brain, in contrast to ECOG that you may know, which is recording at the surface of the brain. We're actually having very deep recordings. And that gives us a ground truth to which we can compare non-invasive results, so MEG, SQUID, or OPM, to these recordings performed within the cortex. And as Denis was mentioning, we perform a simultaneous MEG and intracerebral recordings in the team. So the pioneering work was done by Anne-Sophie Dubarry, who is presented on the left, who during her PhD thesis recorded actually 3 modalities together, not 2, but 3, EEG, MEG, and intracerebral EEG. So that was the proof of concept that we can measure from outside of the brain and within the brain at the same time. And the technique has been modified with especially the contact points. I mean, the fixation points of SEEG was a tricky part, and also the amplifier that we use have been changed. But now we are in the process of doing it in a regular basis. Why should we go to simultaneous recordings? Because we want to measure exactly the same activity outside of the head and within the brain. And in epilepsy, it's very important because the discharges we measure, the epileptic discharges, are very variable in time. They vary in terms of extent of brain that is involved. There can be also changes in medication level between 2 different sessions. But it's also important in cognitive paradigms because we may want to record the exact same brain state, the same level of attention, memory also. Once you've memorized something, you cannot do it again. And also, very importantly, because we want to use the fluctuation of activity as a source of information. So you see here a single trial analysis performed by Anne-Sophie, where you can actually do the correlation across trials of activity to find the relationship between the 2 types of signals. And this you can do only with the simultaneous recordings. That's an example of a simultaneous recording. So on top you have the MEG signals, and in the bottom graph the SEG. So you can see the beauty of it, seeing these two huge epileptic spikes. I don't know if I have a pointer. Can you see my pointer? Yes, you can. Okay, so that's the big discharges. You see a big network involved in the depth, and you see a beautiful epileptic spike at the surface. And when you have a small discharge like here, you cannot see it visually. So these simultaneous recordings, they show in which condition we can see something on the surface. And also they allow us to progress in the signal processing to be able to extract very subtle activity from the surface. One application is the visibility of deep sources. It's a long-lasting question in epilepsy and in EEG and MEG in general. Can we see the deep structures like hippocampus, amygdala, thalamus? And as we have a recording directly within the structure, we can really test that. So here, to our surprise, we saw amygdala activity. We really checked it thoroughly because we didn't believe it in the beginning. And you see the topography of this activity. This is an ICA component. It's very wide, very widespread, and it really shows from the topography that you have a deep source. And if you do source localization, you localize it deeply. And the correlation between the MEG activity and the intracerebral EEG shows a very beautiful correlation within the amygdala. We did other applications. So Nathalie Georges, when we first presented the epilepsy, said this is too easy because you have big epileptic spikes. You should go to cognition. So we tried it. We did it. So this is a visual recognition task where we saw correlation between the activity in MEG and deep structures such as rhinal cortex. So we can also see deep structures in cognition with MEG. And this is a study with the correlation of connectivity measures between MEG and SEG. So now I'm getting to the main topic because I'm in the OPM track, and that's what we want to go to, use OPM to measure epileptic and cognitive activity and correlate it with depth recordings. So as mentioned in the previous talks, OPM offer new possibilities, long-term recordings, seizures, that potentially gives us access to seizures that happen very rarely. So that's very important in epilepsy. We can have custom sensor position and, as mentioned, also easier recording with children. We're using helium OPM that have a large dynamic range, large frequency bandwidth, also very important in epilepsy because we're interested in high frequency oscillations, and negligible heat dissipation, so we can have high spatial sampling. So this is the simultaneous OPM and intracerebral EEG project. So I have to say I'm really a second line in this project. It's really the work of Jean-Michel Badier, Francesca Bonini at the INS, Denis Schwartz here, Etienne Laby, Augustine Palacios-Laloy from Mac for Health. So they did these recordings within an INR project, MIO. And the idea, so the objective was to validate the capacity of helium OPM to capture epileptic discharges with two setups, so SQUID SEG and OPM SEG. So the two simultaneous recordings were doing either the SQUID with intracerebral EEG, and in the second part, OPM with intracerebral EEG. And it's the SEG that allows doing the comparison between the two, as unfortunately we cannot do OPM and SQUID at the same time, but that's the best that can be done. So that's again the setup. It's a tricky setup, obviously, that the classical now SQUID and SEG and the OPM sitting on top of the SEG setup. And the idea was to find the sensors, the SQUID sensors, so as mentioned in the previous talk, that are closer to the OPM sensors in order to compare the SQUID signal and the OPM signal. So the events were matched between the SQUID session and the OPM session. So visually, there was a matching of the extent of the epileptic network in the discharges, because as I mentioned, epileptic discharges can have very varied extent of involvement of different brain structures. So you need to very carefully match the discharges to study the same event types. And this is the event measured on the SQUID on the left and on OPM on the right. So From here, you can see that the OPM signal is higher in amplitude, but the noise is higher also. Well, it's probably a mixture of signal and noise, but what really counts is the signal-to-noise ratio of activity. We see the spike has a very nice shape on the OPM compared to the squid. And also something we see, you have in blue the radial component and in red the tangential component. You can see that the two components are not the same. So it's a very important point I'm going to insist. So there may be a diversity of recording that may add new information to the recording. So that's one type of epileptic spike. So Jean-Michel, Francesca selected different types of activity that are representative of the activity in this patient. So one involves the temporal pole. It's really a beautiful spike in a temporal pole electrode, TP electrode. And it's visible in both squid and OPM. There could be a higher diversity here, but it's not completely obvious. Maybe, yeah, there's one signal that's different, but it's the same timing, so not so clear here. But we have a nice view, and the SNR is higher in the OPM. That's a large network involved. That happens very often with epileptic spikes. So here you see that the OPM in this case has a much nicer signal-to-noise ratio. And there you can see diversity with the timing. You see that the peaks are not at the same time in the radial component here and tangential component there. And also higher signal-to-noise ratio. Oops, now that's sad news that in this case, in a hippocampal spike, wasn't very visible on neither OPM or squid. Maybe there's this low frequency activity on the squid, but on the OPM we cannot see it. That's a summary of the SNR for different configurations. So the different types of spikes, 1, 2, 3, 4. 3 and 4 are the deep mesial spikes involving the hippocampus and have a low SNR. And the other ones are the larger, either large network or the temporal pole I presented. And then we see that the radial OPM has a very nice signal-to-noise ratio. So the conclusions is that this is the first direct validation of the ability of helium sensors to record epileptic activities. So with this ground truth of intracerebral EEG. We obtain high SNR values, so that's very good news. That was performed, so that's a very important point. Now, I should really insist. This is done in a regular clinical environment and there is no advanced noise correction. So I should have mentioned that earlier, that all the signals from OPM had only very basic filtering, bandpass filtering. But so it's kind of unfair because the OPM has the reference sensors that are subtracted from the signals, where here there is no such processing. So Laurent Hugueville is here in the room, is going to collaborate within the MEO project to apply noise correction to the OPM. So we expect that with a full helmet, there will be new capacities to remove the noise, to filter out the noise. And also, I think a very nice point is that there is complementary information from the tangential components, potentially complementary. So that's very important in the sampling question that was asked by Françoise, because maybe we can get, even if we have less sensors, we can get information from the tangential components that can help the undersampling of the fields, because probably 100 sensors is undersampling, but maybe the tangential component will compensate. And that was done by, simulations done by Tim Tierney in London showed that in principle, you can recover activity from the tangential components, so improve the source localization. So future direction, there is this very nice subject here. He looks very happy to be with OPM. So future directions are the use of full head systems, so 48 and pushing it hopefully to 96 channels. Actually 96 sensors, sorry, not channels, because there are 3 components per OPM. So that's much more channels. We would like to investigate the deep structures, see maybe with the denoising. And that's my third point. The denoising technique will help, hopefully, seeing better in depth. And that requires a lot of channels. Now the studies on a few channels, much more difficult to denoise. So I want to thank the whole team, the whole Dynamap team from INS involved in part of these studies. Thank you very much. And thank you. And the founding organizations. Okay, thanks a lot. I'm open to questions if you have.
Thank you very much, Christian.